All right, cool. Hello everybody. So today what we're gonna be doing is we're just gonna be talking about as you can see, the Chinese remainder theorem. So this theorem is a really useful one to use for like constructions. If you have like a problem, trying to prove that something exists, if you can get the statement into something that you can use the theorem for, it'll be really useful. So I think what we'll do first is we will just have a little experiment first, right? So if we have a look at this series of congruences, um, so it'll be x is congruent to 2 mod 7, and also x is congruent to 1 mod 3, right? So if we have a look at this, like these two congruences, and we want to try to find values of x that satisfy both of them. Um, Once we get more used to these kind of things, it will lead on to the theorem very nicely. Okay. So let's just have a look at this one first. So if x is congruent to 2 mod 7, we will have x must be in the set. So x must be in the set of, let's see, I'll go from the negative. So there's a bunch of negative numbers. It must be in the set of negative 19, because um that's 2 away from 21, which is a multiple of 7. And then we go to negative 12, negative 5, and then 2. And then we go into the positives to that side. So 2, 9, 2, 9, 16, 23, 30, and then it can keep going forever, right? You can see this. So x must be in this set. So negative 19, 12, blah, blah, blah. If x is in this set, then we know that x satisfies this first condition. And then we also know something else, right? We also know that x must be in another set, and that is 1 mod 3. So that must be a bunch of negative numbers. It can go all the way that way. Negative 8, negative 5, negative 2, 1, 4, 7, 10, etc. So x must also be in this set. So I guess then we see that while x must satisfy both of these things, right? So if we call this set A and we call this set B, then we just have the condition that x must be in the set of A intersect B, right? X intersect B. So this symbol just means I'm taking the elements that are common to both of these sets, and then we're saying x must be um in that set of intersection. Okay, so what we can actually see is that if we look at the elements in this set, they are in an arithmetic progression, right? And their common difference. So this element in the set A and B are in an arithmetic progression. And common difference is equal to, is equal to 3 times 7, which equals to 21. Here we go. Why is that? It will be a lot more clear as we go on. Okay. So that's kind of like the first little example I wanted to go through. And then what we can do is because there are a few more cases, right? Something special about 3 and 7 is that they're both prime. There are some other special cases. So for example, if we consider another set of congruences, if we have, let's see, x is congruent to 1 mod 3, and then x is congruent to 1 mod 6. You might like suspect that these two situations will be a little bit different. So this one and this one will be a little bit different. Why is that, right? Because like I've said before, 7 and 3, they're kind of primes, but 3 and 6 are not really co-prime. There's kind of like some relation in how 3 divides into 6. So if we have a look at the sets here, X must belong in the set. So we start off with the 1 mod 3 set, which is just the same one as above. This one. Oops. This one. Which is, let's see, -8, -5, -2, 1, 4, 7, 10, dot, dot, dot. And it also goes dot, dot, dot the other way. So X must be in the set. And then at the same time, X must also be in this set, which is, so obviously 1 will work, and then go 7, 13, dot, dot, to the positives. And then the negatives, it will be -5, -11, -17, dot, dot, dot to the other side. Okay, cool. So if now we look at these two sets intersected with each other, you kind of see the common elements. This one, whoops, this one, and this one, stuff like that. So you can kind of actually see that the solution set is X is just -5, 1, 7, and then you're going up by 6 that way, and then down by 6 in that way. Whoops, no, that's not what I meant. Yeah, so X can be in this infinite set here. I know it will satisfy both of these congruences. Now, now that's like really cool, but also weird, right? Because X, the solution set is exactly the same as this one. Because if you imagine every single set in the second one, in this one, gets mapped into the first one, right? There is a corresponding element in the first set for every element in the second set. Why is that, right? Because if we imagine something like X is equal to 6K plus 1, then you automatically already know that 3 must also divide. Oops, I'll write it this way. Then you just already know that 3 must divide x minus 1, right? Because obviously 6 is a multiple of 3, and yeah, that's kind of like why. And then there's one final case I want to talk about, and that will be this set of congruences. X congruent to 1 mod 6, and X congruent to 2 mod 9. And you can really like replace 2 here with anything as long as it's not 1 mod 6. What I mean by that is if we just look at what numbers work, right? X is in this set of, actually I'll just ignore the negative numbers. I'll start from 1 because it's easier. X is in the set of, so the negative numbers, and you go 1, 7, 13, 19, dot, dot, dot. So you're adding 6 up each time. And X also must be in 2, sorry, must be in the negatives, like the negatives that way. And then 2, 11, 20, 29, and you're going up by 9, right? Cool. And now you try to find the common element between these two sets, and you might realize that you can try as hard as you want, you can go up as many elements as you want, but there will not be a singular common element in both of these sets. Why is that, right? Why do sometimes there are no solutions to the series of congruences? That is actually because if you think about X in algebraic terms, right? If you represent X in algebra, we have 6K plus 1 for some K. But then X also equal to 9. I'll use a different variable, right? 9L plus 2. Now, these two are equal. So if we write 6K plus 1 is equal to 9L plus 2, that will be the same as saying oops. That will be the same as saying 6k is equal to 9l plus 1. And now that's something really strange, right? Because the left-hand side is divisible by 3. But the right-hand side is 1 mod 3. The 3 does not divide the right-hand side. So the two sides can never be equal. So they can never be an element of x. There can never be an element of x that satisfies both of these things. Okay, so what we've done is, if we just look back here, so we've got this case, and this case. So we've gone through 3 cases, and that's just 2 congruences. And what the Chinese remainder theorem tells us is that we can generalize this to any number of congruences. So we have n of these congruences, and it tells us when it's going to have a solution and when it's not going to have a solution. So the actual theorem goes as follows. I'll write it here. I'll write it in blue. Chinese remainder theorem. Cool. So the theorem goes as follows. For integers and for integers a1, a2, an. So we have n integers and pairwise coprime. So pairwise coprime integers b1, b2, bn. So that's just n numbers, n like any integers in the A's, and then the n numbers for the B's must be pairwise coprime. So any 2 of them have a greatest common divisor of 1. There exists exactly one solution of x. There exists exactly one solution of x under mod b1, b2, bn. So that's mod of the product of the b's such that x is congruent to a1, a1 mod b1. X is congruent to a2 mod b2. Whoops, what's happening? X is congruent to a2 mod b2. And then that goes all the way to x is congruent to an mod bn. Okay, so this is the statement of the theorem itself. So I'll just explain more what that means. So you have any n integers, and you have any n pairwise coprime integers. And then the theorem says that there is exactly one solution of x under the mod of the product of the b's, such that these series of congruences are satisfied. So if we have a look back at our original example, this is just the case for n equals 2, right? We have exactly 2 congruences. And the b1 and the b2 here are 7 and 3. And the pairwise coprime. And then 1 and 2 are just the 2 random integers that we can have. So we have these 2, and we have these conditions in that b1 and b2 are coprime. So we can actually use our Chinese remainder theorem here to say that, well, there is exactly one solution under mod 3 times 7 under mod 21, such that this is satisfied. And that is exactly why the solution here have a common difference of 21, because all of the x that satisfy these must leave the same remainder when they're divided by 21. In other words, they are arithmetic progression with common difference 21. So that's the n equals 2 case. And the cases here don't work because what, as you can see, 3 and 6, they are not co-prime, right? Because the greatest common divisor is not 1. And similarly for 6 and 9, the common divisor, like the greatest common divisor, is not 1. So the Chinese Riemann theorem actually does not apply here. But that's just like intuition for how the theorem actually works. So we must be able to prove the theorem, right? And to prove the theorem, there's actually two parts. So if you notice how here it says exactly one solution of X, that actually means we have to prove there exists at least one solution of X. And then we also have to prove there exists only one solution of X. So that's the two parts of the theorem that we actually need to prove. So we can go and do that now, right? Proof of CRT. And CRT is just like a shorthand notation for Chinese remainder theorem. Proof of CRT. And we will actually first prove uniqueness. Let's first prove uniqueness. Well, let's prove uniqueness. Okay. And that's just saying there should be only one solution that satisfies this. Like there cannot be more than one solution that satisfies this. So let's suppose we have numbers x and y. And the numbers x and y both satisfy this little bit, like this thing here. So in other words, we got x is congruent to 1, a1, bracket mod b1, x is congruent to a2, mod b2, and a dot 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 all the way down. And a y is also congruent to a1 under mod b1, stuff like that. And it just keeps going down. In other words, what we have is actually x is congruent to a1, but a1 is also congruent to y. That is also congruent to y under mod b1. That's just using the condition that if we suppose, actually I'll write, for the sake of contradiction, suppose we got xy to satisfy this, because we want to prove that we want to prove that it doesn't work, right? So we have x congruent to a1, congruent to y under mod b1. And what we'll do is we can just take this and take this, and we can say x minus y congruent to 0 mod b1. And in other words, this implies essentially it's equivalent to b1 divides x minus y. This is what we can say because they leave a remainder of 0 when divided by b1. And similarly, because the subscript of 1 actually doesn't mean anything. So we have x also congruent to a2, congruent to y under mod b2, under mod b2, and that will imply b2 divides x minus y as well. Okay, and you can in fact continue this pattern down all the way to b and divide x minus y. Cool. So we got all the b's actually divide the difference between x and y. But there's also one more condition. The bi, bj are co-prime for any I and j. Right? So we have the b's are pairwise co-prime. And well, if every single one of these divide the difference, divide x minus y, and they're also co-prime, we must have b1 times b2 times b3 dot 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 all the way times the bn divide x minus y. Why? Because since they're co-prime, they got no common prime divisors. And so the prime divisors in b1 must divide x minus y. And then a different set of prime divisors in B2 must also divide x minus y. And then another set for B3 divides x minus y, and so on. So in fact, if we have all of these numbers times together, the prime divisors in there will be different, and they must all divide x minus y. Cool. I'll just rewrite this as n equals to this divides x minus y, so that's big N. What does that mean? Well, that means x must be congruent to y under mod big N, right? But wait, we have assumed that x and y are different. That is one of the assumptions, because we're trying to prove that there are more than one solution. And also, the assumption is that they are less than mod n. Why is that? Because the theorem says that we are looking at it under mod b1, b2, all the way to bn. And that's just mod big N, right? So we actually have x, y is less than big N, and x congruent to y under mod n. And that is actually, in fact, enough to conclude that x is equal to y. And that's bad, right? Because we had assumed that x and y are different up here. We deducted, and then we end up at a result of x equals y. So that would be a contradiction. So the contradiction just means that, okay, there are not more than one solution to the series of congruences. So we're done with uniqueness. Yeah. Okay. And now let's go and prove existence. So what does that mean? Existence just means we want to prove that given any of these numbers, there will always be at least one solution. So proof of existence. Proof of existence, yeah. So what we want to do is we'll do a trick called proof by induction. Proof by induction. And specifically we want to induct on n, small n, and that's the number of congruences we got to satisfy. Well, first of all, n equals 1 is trivial, right? You just take x is equal to a1, and then you'll be done. Because there's only one congruence to satisfy. You just take any x is equal to a1 under mod b1, and you're done. So the more interesting case is n equals to 2, which was what we did at the very start. But now we're going to do it generally, right? So we must have x satisfies a1 under mod b1, and also x satisfies a2 under mod b2. Okay. We have this bit of this information I'm going to use, and also GCD of b1. Whoopsies. GCD of b1 and b2 equal to 1. That is another one of our conditions. Okay. So what I'll do is I will quote a theorem which is called Bezout's lemma. And I've actually talked about this before, I believe. So Bezout's lemma just says we have numbers m1 and m2 such that m1 times b1 plus m2 times b2 is equal to 1. So m1 and m2 can be any integer. So they can be negative integers or positive integers. But there must exist m1 and m2 such that this thing is satisfied. So now we have this. Let's construct. Let's actually just construct an x that works for this, right? What I'll do is I'll take x is equal to a1. So that's the a1 up here, right? That's the a1 up here. a1 times m2 times B2 plus A2 times M1 times B1. This will be my X. Yeah, so this will be my X, and I want to prove that this X satisfies both of these conditions. So let's have a look, right? What I can do is I can substitute for M2B2 with this formula. So X is actually equal to A1 times 1 minus M1 B1 plus A2 times M1 B1, right? So I've just substituted the M2 B2 with 1 minus M1 B1. Okay, let's expand this. So we have that is equal to A1 minus A1 M1 B1 plus A2 M1 B1. And we can factorize out M1 B1, right? So A1 minus M1 B1 bracket A2 minus A1. So I've just factored the M1 B1 out. And now if we look at it, we have a B1 here. So that will go away when we take mod B1, right? So here we actually have X is congruent to A1 under mod B1. Because if you divide by B1 the last term, this term just cancels out. Okay. This term just cancels out. And similarly, what you can do is you can substitute 1 minus M2 B2 into this one here. And you do the same logic and you'll get the other congruence, right? I probably won't do that here because it's literally the exact same thing as this one. But we have that X is equal to this thing will satisfy both of these congruences. So we have found a solution. That's basically what I'm trying to say, right? We have found a solution such that this thing works. But also by our work up here, right, by our work up here, we actually know that there cannot be more than one solution. So if there cannot be more than one solution and we found one, then there must be exactly one solution to this congruence when n is 2. And that's our base case for the induction. That's our base case. I can write base case. Done. And let's go to the inductive hypothesis, which is just to assume there is a solution. Oops. Assume there is a solution to X congruent to A1 whoops, what's happening? X is congruent to A1 mod B1, X congruent to A2 mod B2 dot 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 X is congruent to AN mod BN. So we're just assuming that the N case is true and we're trying to prove the N plus 1 case. So inductive step, prove N plus 1 case. How might we do this, right? So we have all of this up here. I'm just gonna copy that. Oh my God. Yeah, I'm just gonna copy that down here. And we also have a extra congruence, a n plus 1 mod b n plus 1. Okay, so we want to prove that this is true. So we can use our hypothesis first, because the first n are just the random n's and it should hold true for any values of a and b, right? So there must be a singular x that satisfies all of these. So, and from the result of the Chinese remainder theorem, we have that x must be congruent to some value on the mod b1, b2, b3, dot, 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 bn. Right? That some value, I'll just write it as x is congruent to, I'll just call it big K on the mod big N. Where K and N are just some values that I don't really care about. So now guess what? We're back at solving two of these congruences, right? So we just have x congruent to big K on the mod big N, and x is congruent to a n plus 1 on the mod. Oops. On the mod b n plus 1. And actually, if we look at this, it's literally just our n equals 2 base case that we have done here. So that's what we can do. We just have this, and we can just say true by base case n equals 2. Cool. So we have actually just finished our induction, and we have found a solution for every n possible. So what I'm saying is that for any value of n, there will always exist a solution of x, such that this series of congruences is satisfied. But there can also not be more than one solution without proof by uniqueness. So that limits the number of solutions to exactly one. And that's exactly what we wanted to prove, right? We wanted to prove that there's exactly one solution to this. So now we are done. Okay. So now we have the theorem. I think it's good to do a few practice problems on the theorem, right? Now we're gonna have some practice. So practice problems. So problem 1 will be this problem. Okay. We want to show that for any C, which is a integer, and a prime P. Whoops. Any C which is an integer and a prime P, there exists X such that X to the X is congruent to C on the mod P, where P is a prime. Yeah, okay, so that's the first problem. Basically, what we're saying is that I'm trying to find a solution such that this thing to the power of itself is congruent to C, where C is anything under a prime mod. So how might we go about doing this question, right? My first thought when I see this is that, well, wait, we have a prime modulus. So if we have a prime modulus, then a result that we should probably use is called Fermat's little theorem. Well, I'll just write FLT. And that tells us that x to the p minus 1 will be congruent to 1 on the mod p. And that is very useful, right? If we think back to the lesson about orders, that is one of the very useful results that we use there as well. So we can actually see that x to the power of k times p minus 1 will always be congruent to 1 mod p. Okay, So that will always be congruent to 1 mod p. So what does that mean? It just means that the exponent of x, when I do x to the x here, it only really matters if we look at the remainder when it's divided by p minus 1. So the power of x kind of cycles every p minus 1 times, right? So it would be very good if we can somehow control this x, right? If we can somehow control this x so that we are ending up with a value, which is c. So what we actually want, and I'll write the congruences here. So we actually want x is congruent to 1 under mod p minus 1. And I'll tell you guys why later, right? So, and we also want x is congruent to c under mod p. So why is that? Why is that, right? So that is because since the power of x up here, it will cycle once every p minus 1 times. So if we cycle through this x p minus 1 times, and we are left with one more x, then we can just have x here by itself, right? Yeah, so if we cycle through the exponent p minus 1 times, the remainder is 1, so we'll just be left with 1 times itself a bunch of times, times x to the power of 1, which is x. And that is where the second condition comes in. The second condition just tells us, okay, well, if we can just control x to have only one power on the left, then why don't we just set the x to be the number we want? And then we'll be done. So what we realize now here that, wait, GCD of p and p minus 1 is exactly 1, right? There must be co-prime since they're consecutive numbers. So now if they are consecutive numbers, we can actually say, therefore x exists by Chinese remainder theorem. Where we just have c and 1 are just some random integers, and we have p minus 1 as b1 and p as b2. So x must exist by Chinese remainder theorem. Now, you will write it out like this to finish the problem. So you will write it up like x to the x must be congruent. Must be congruent to x to the power of k. Actually, it's not even congruent, it's equal. K times p minus 1 plus 1. Why is that, right? Because we know that x satisfies 1 mod p minus 1, so it must be some multiple of p minus 1 plus 1. And I'll do the transformation here, which is just x to the k times p minus 1 times x, which is equal to x to the p minus 1 all to the power of k times x, where k is just some integers. Yeah. All right. So k is just some integers here. And now I am looking under mod. So I'll use the triple equal, which is the congruent sign. That will be congruent to 1 to the power of k times x mod p. Because this step is just by FLT. And I'll just be congruent to x mod p. So if we have that equal to x mod p, but here we also have x satisfies c mod p. So then we just have that is congruent to c under mod p. Yeah. That's actually the entire solution to this problem, right? So we want to show that for any c and z, we got this thing. So then we changed it into a way where we can use the CRT. And specifically here, it's the n equals 2 case, right? So the n equals 2 case, and we have the CRT here. And we can literally just quote, okay, we know that x must exist because of this Chinese remainder theorem, which we proved above. And then from there, you can kind of just like manipulate the stuff down and you'll get your result. So that is good. So that is this problem done. Another problem I want to try is this one. So if you go down here, problem 2. This might be really cool. So we want to find what is the last 2 digits of 49 to the power of 19. So that's just some really big number. You can kind of like do this for any number really. So what is the last, actually, what are the last 2? What are the last 2 digits of 49 to the 19? So when I see this problem, what I think about is, well, I'm trying to find the last 2 digits. So that is just equivalent as me finding 49 to the 19 congruent to what under mod 100, right? Because to find the last 2 digits, you can literally just take the remainder when you divide by 100. But what we need to note is that 100 is equal to 4 times 25. And the important thing is that the GCD of 4 and 25 must be 1. So that's the important thing. So we can kind of think about this like in this way. So if we have 49 to the 19 congruent to what under mod 4, and 49 to the 19 congruent to what under, whoops, what's happening? Congruent to what under mod 25, right? Let's say this thing is congruent to like 3 under mod 4, and this thing is congruent to like 10 under mod 25, right? And you have X that satisfies both of these conditions. Then you can use your CRT again to get X must be a specific residue class under mod 4 times 25, which is under mod 100. And that is exactly what we want. Okay, so that is exactly what we want. So I guess first step is we want to try to find, okay, what are these values exactly, right? What are the 2 question marks exactly? So I can tell you that 49 to the 19 is congruent to 1 to the 19, which is congruent to 1 under mod 4. And that is just because 49 itself is 1 mod 4, right? 49 is 48 plus 1. 48 is a multiple of 4, so it's just going to be 1 to the power of 19, which is just congruent to 1 mod 4. But also 49 to the 19 is congruent to negative 1 to the power of 19, which is congruent to negative 1 mod 25. Why is that, right? 49 is 1 away from 50, and so that's negative 1 under mod 25. And then we have negative 1 to itself, to the power of itself 19 times. That gives you negative 1 under mod 25. In other words, we want to find X congruent to 1 under mod 4, and also X congruent to negative 1 under mod 25. And just to explain what I said earlier, there must be a unique solution of X under mod 100, under mod 2 times 25. That's just CRT. And that unique solution is the one we want. That is the one we want because X will be congruent to 49 to the 19 under mod 4 and also congruent to 49 to the 19 under mod 25. So that is the value we want. And how do we do that exactly? Like, how can we find what value of X satisfies this, right? And that is when we think back to all the way up here. I'll work with the base case n equals 2 because well we have n equals 2. down here in the practice problem. So n equals 2. We have this construction. We had this construction which worked. So we want to find two values of m1 and m2 such that Bezout's lemma holds. I can just tell you that the values here are x. If we take x to be equal to, let's see, if we take x to be equal to -1 times 4 times 19 plus 1 times 25 times 1. Right. Let's see. I don't think that works exactly. No, it does. Okay. So we have, if we take x equals to this value, then we just have minus, what is this? Minus 76 plus 25. And that will be equal to minus 51, I believe. So minus 51 under mod 100. Oops. Minus 51 under mod 100 is our unique solution. And that will be congruent to 49 under mod 100. So yeah, actually what we have here is that the last two digits of x will be 49. And then x is actually just congruent to 49 to the 19 under mod 100. So the last two digits of 49 to the 19, last two digits of 49 to the 19 is, oops, I'm writing it here. Last two digits of 49 to the 19 is 49. Yeah, okay. Ooh, I think that's all I have for today. Yeah, so just like an overview, we started off the class, right, with some base cases. So we kind of like had a bit of intuition for the n equals 2 case of Chinese remainder theorem. Then we kind of like proved it. We did the statement and then we proved the theorem in two parts, right? We first proved uniqueness of the theorem, and then we went again and proved the existence of the theorem. So now we must have exactly one solution for this congruences. And then we went through two practice problems. One of them, we kind of analyze the pattern in the exponent when it loops around. When it loops around in cycles of p minus 1. And another one is just computational, where we compute the last two digits of this thing on the mod 100. Okay, yeah. So that's all of this for today. Thank you everybody for coming, and yeah, I'll see you guys next time. Thank you.